Good evening. Uh, Now we're going into the next topic, that is Young's double slit experiment. It's the next derivation under the topic on interference. So in interference, in the last session we did the derivation for conditions for constructive and destructive interference. That is, when does P become bright, or what is the condition for P to be a bright band? We know that this path difference, which we call as delta, we call that path difference as delta. If it is an integral multiple of lambda, n lambda, we know that P is going to be a bright fringe or bright band. If this delta, or the path difference between the two waves arriving at P from S1 and S2, which are coherent sources, happens to be an odd multiple of lambda by 2, then P is going to be a dark fringe or a dark band. Now, this is the experimental setup of Young's double slit experiment. It's called the double slit experiment. Like in my previous session, I told you, we have two sources here, which is lit by the same source. So, from the same source S, we have light arriving at the two pinholes on this screen that he has taken, and S1 and S2, because they are lit by the same source S, happen to be coherent because they have the same frequency, same wavelength, and also maintain a constant phase difference. Now, when these waves from S1 and S2 reach P, they can have a path difference, and if that path difference is an integral multiple of lambda, then I said P is going to be a bright band. If this path difference is an integral odd multiple of lambda by 2, then P becomes a dark band. What we are now going to do is, so we know that this phenomenon of interference will produce on the screen, which is placed at a distance d from the double slit, will have alternate dark and bright fringes because of the superposition of waves from the coherent sources, that is S1 and S2. So today's derivation, what we're going to do is derive an expression for what we call as beta, that is the band width, which is the beta is the bandwidth, that is width of a bright band. Width of a dark band is also called beta. So we are now going to derive an expression for the linear bandwidth, or simply the bandwidth of either a bright band or a dark band. So in this, what we are actually going to do is, see, suppose this is the center of the screen, okay? So we have alternate dark and bright fringes here, and we see, I've shown you here that P is a position of either a bright or a dark depending on the path difference. So if I can, let's say this is going to be a bright band. I'm going to find the expression for Y for a bright band. The next consecutive bright band is going to appear here. So if I take this as, let's say, Y2, this is the first bright band, this is the second bright band, and this is the third bright band. So if I get the expression for Y2 and expression for Y3, I may subtract Y3 minus Y2. So between two bright bands, I will get the width of a dark band, which is going to be beta. So basically, we are going to find out an expression for Y, which is a distance of a bright band from the center of the screen. Subtract two consecutive Y for bright band, get the width of one dark band, because between two consecutive bright bands, we will have one dark band. Or to find out the width of a bright band, what you can do is, you find the expression for Y for, let's say this is the second bright band. For Y2, this is the first bright band, that is Y1. Subtract Y2 minus Y1. In between two dark bands, we have a bright band. So you get the beta of a bright band by simply subtracting the Y for two. If suppose this is dark, between two consecutive dark bands, you will get the width of a bright band. So we are now first going to find an expression for Y. Okay. So here we start with this path difference delta, because we know delta is n lambda for bright and delta is 2n plus 1 lambda by 2 for dark. So knowing that condition, we will now find an expression for delta in terms of Y, capital D and small d. Small d is the distance between the two coherent sources. Y is the distance from the center of the screen to the nth bright or dark fringe. So here I may write S2P minus S1P is what I want. That is delta. S2P minus S1P is going to give me delta. But I cannot directly get S2P minus S1P. So I'm going to square it so I can apply Pythagoras theorem. So from this big triangle here, you will see S2P square is D square plus this distance, that is Y plus D by 2. Because this is D and this is the center, this much is D by 2, this is also D by 2. So I may write S2P square from this big triangle is going to be D square plus Y plus D by 2 the whole square minus S1P from this small triangle will be D square plus this distance, which is Y minus D by 2. So I may write D square plus Y minus D by 2 the whole square. If you open the bracket and cancel everything, you will see that S2P square minus S1P square is going to be 2YD. You open the bracket and you cancel the D square here and D square here and all that, you will get 2YD. Or this I can write as A square minus B square is A plus B into A minus B. So I may write this as S2P minus S1P is 2YD by S2P plus S1P. That is, I took this A minus B here and brought the A plus B here. Now I may approximate S2P to be approximately equal to S1P, assuming that this Y and this D is much smaller than capital D. That is, if the screen is really far away, you may take this, these coherent sources are actually very close to each other and the fringes are also close to each other. So I may approximate D and V to be, this Y to be small compared to capital D. For example, let us see if you take, let's say we have a screen, this is S1, this is S2 and this distance is only 0.1 centimeter. This capital D is, let's say, 100 centimeter. And do it here. So the approximation is, say I have a screen which is placed D equal to 100 centimeter. Okay. Now these two D is going to be equal to, let's say, 0.1 centimeter. 0.1 centimeter. So that I take one here from another one here. So this much is half of D. So that will be 0.05 and this is also that 0.05 and let's say this Y from the center of the screen. This Y is equal to, let's say, 1 centimeter. So now S2P is going to be equal to, this is S1P and this is S2P. So from this big triangle here, I may write S2P as 100 square plus the base, 100 square plus from here till here 1 plus here, this is 1.05 the whole square, the whole raised to half because it should be the square root. Now S1P, if I substitute in my example, S1P from this triangle here, the base is 100 and so this is 100 square plus this much only. I need only this distance, that is 1 minus 0.5 will be 0.95 the whole square root of that. If I add now this S2P and S1P, you will see you are going to get 200.01 centimeter. If you calculate and see, you will see that this S2P plus S1P is 200.01 centimeter. So you will notice that we have taken small d as 0.1, this Y as 1, but D is 100. So D is much larger than small d and Y. In such a case, you will see that S2P plus S1P is around 200 plus 1, which means in our equation here, where we got this as 2YD by S2P plus S1P, right? This S2P plus S1P is what I said after calculation, 200.01 centimeter if D and Y are much smaller than capital D, which means I can approximate this to capital D, right? Because capital D is 100 in our example. So if I write 100 and 100 here, I get a 200, which is very close to 200.01. So I may approximately write S2P is S2P almost equal to S1P, which I will take as D, capital D, equal to capital D. So I can't do that here, because if I do that here, then this becomes 0. So on the right hand side, I'll take the assumption and I may write this S2P minus S1P. S2P minus S1P is what we have as delta. So I may write that as delta is equal to 2YD by D plus D, that is 2D, and I get this as YD by capital D. Okay. So now I've got a relation between Y, which is the distance from the center of the screen to the nth bright or dark band. I've got small d, which is the distance between the coherent sources, capital D, which is the distance between the double slit and the screen, and delta being the path difference between the two waves that arrive at P. So now I may write, I have to now find out the bandwidth, right? I need to find an expression for Y. So now if I'm going to take a bright band, for the bright band, we already know from the previous derivation that delta condition is n lambda. This we did in the previous derivation, in the last session. So now we also know that this delta is equal to YD by capital D. Just now we showed. Or we may equate this and write YD by capital D is equal to n lambda, or Y is equal to n lambda capital D by small d. Okay. Now I said once you get Y, you can subtract two consecutive bright. So this is the expression for what? This is a bright band. So it is the expression for the distance of the nth bright band from the center of the screen. Where is it going to arrive? So if I subtract two consecutive bright bands, between two consecutive bright band we have a dark band, I'll get the width of a dark band. So I may write Y equal to, I can write, beta is equal to Y2 minus Y1, or Y3 minus Y2, or Y4 minus Y3, or Yn minus Yn minus 1. You can write it in any way you want. So if I substitute Y2 and the second one, so if I put 2 here, this is 2 lambda d by small d. For the first bright band, it will be 1 here minus lambda d by small d, and I get 2 is lambda d by d. So you see the width, the fringe width or the bandwidth of a bright band is lambda capital D by small d. Lambda being the wavelength of light, capital D the distance from the double slit to the screen, and small d is the distance between the two coherent sources. The same thing if you're going to repeat for dark band. Okay, I want to find the width of a bright band. So I need to find the Y for a dark band, subtract two consecutive Y for dark band and get the width of a bright band. So the condition in the previous session we found for dark band to be at P is this delta must be an odd multiple of lambda by 2. So I may now write, YD by D is equal to 2n plus 1 lambda by 2, or I get this Y to be equal to 2n plus 1 lambda D by 2D. Lambda D by 2D. So I may to find beta. Now this is the Y, that is Y distance of the nth dark band from the center of the screen. So if I subtract the Y for two consecutive dark bands, between two consecutive dark bands we have a bright band, so we get the width of a bright band. So I'm going to substitute and show you. If I'm going to do Y2 minus Y1, here you can do Y2 minus Y1, Y3 minus Y2, or Yn minus Yn minus 1. You will see if I put 2 here, this is 4 plus 1, 5 lambda d by 2d. So 5 lambda d by 2d. And then if I put 1 here, that will be 3 lambda d by, so 3 lambda d by 2d, and you get this as lambda d by d. You will see that the fringe width for the dark band and the bright band are the same, which is lambda d by d. Okay. Now one more thing, so this is called the linear fringe width, or which is lambda d by d. Now on the screen, we have this alternate dark and bright fringes, right? So let's say we have this as the coherent source, the two S1 and S2, and we have this as the center of the screen. Let's say these are the alternate dark and bright fringes above and below the center, and so on. Goes on. So this is the fringe width, that is beta. Okay, linear fringe width is a width of a bright band or width of a dark band. So this is what I call as theta, that is the angular fringe width, and this distance we know is equal to capital D. So if I take tan theta for small angles being equal to theta should be equal to opposite side, that is beta by capital D. This is capital D. Beta we know is lambda d by small d into this 1 by d, and you will see theta, the angular fringe width, is simply lambda by small d. So angular fringe width does not depend on capital D, it is simply lambda by small d. So this is called the angular fringe width, beta is called the linear fringe width or linear bandwidth. Thank you.